In this thermochemistry video, we're going to talk about calculating enthalpy using Hess's law of summation. So what is Hess's law of summation? It's the idea that if a reaction takes place in a series of steps, if we know the enthalpy of each of the steps, then we can use those to get the enthalpy of an overall reaction by adding up the enthalpies of the individual steps. So here's an example. We have the reaction of nitrogen plus oxygen to produce nitrogen dioxide. And if we looked at it in one step, we would see that the enthalpy of that reaction is 68 kilojoules per mole. So the question is, how did we get that number? Where did that number come from? We can also look at it in a series of steps. So two reactions that we know the enthalpy of, nitrogen plus oxygen making two nitrogen monoxides, and we know the enthalpy of that reaction is 180 kilojoules per mole. And then the second reaction is two nitrogen monoxides plus oxygen giving us two nitrogen dioxides, and we know the enthalpy of that reaction is negative 112. So we can use these two step reactions to come up with this overall reaction of nitrogen plus oxygen giving us two nitrogen dioxides. And it's a lot like math. When you add two equations together, you just want your terms that aren't in the overall equation to cancel. And so let's see what we can do. So in the first step, we have a couple of things that are in common with the overall reaction. In the first step, we have nitrogen. And that nitrogen is right there. And it's the same as the nitrogen in the overall reaction. We have oxygen, which is also in our overall reaction, but the coefficient is different. And then our product is nitrogen monoxide, which is not in the overall reaction. So somehow that's going to have to disappear. And if we look at the second step, well, there's where it disappears. The nitrogen monoxide becomes a reactant, and it reacts with some oxygen to make two nitrogen dioxides. So essentially what happens is the two nitrogen monoxides made in the first step and then used in the second step disappear, they cancel out, and you end up with an overall reaction when you add the two together of nitrogen plus two oxygens giving us two nitrogen dioxides. And that matches our overall reaction. So how do we get the enthalpy of that? Well, we can just add the enthalpies of each of the subreactions together. So 180 plus negative 112 is going to give us positive 68 kilojoules per mole, which is exactly what we knew what it was. So we can use this concept to find the enthalpy of reactions when we're given several a series of steps for the reactions. And look at what we possibly have to do. There are two things you might possibly have to do with each of your step reactions. You might have to take that reaction and reverse it. For example, if something is a product in the step reaction, but the overall reaction has it as a reactant, all you have to do is just reverse the reaction. And when you reverse the reaction, you're going to have to flip the sign of your enthalpy, because if the original reaction is exothermic, when you flip it, it becomes an endothermic. So all you have to do is flip the sign. So the first thing you might have to do is you might have to flip the reaction, and if you flip the reaction, you flip the sign. The second thing that you might have to do is change the coefficients. So the magnitude of the enthalpy of the reaction is directly proportional to the quantities of the reactants and products, and we talked about that earlier. So if you change the coefficients, well, however you change the coefficients, the same thing has to happen to the enthalpy. So if you have to double a reactant to get it to match the overall reaction, well, then the enthalpy needs to be doubled. So we just call that multiplying. Keep in mind that multiplying by a fraction works. It I understand it's dividing, but let's just make it simple and just always call it multiplying. So 2 possible choices, flip and multiply, and sometimes you might have to do both. An example. So we've got this reaction, the overall reaction is 2NO, nitrogen monoxide, plus oxygen is going to give us dinitrogen tetroxide. And we want to find out what the enthalpy of this reaction is. So we're given 2 stepwise reactions. So let me fix this because for some reason there's not a 2 here. All right, so reaction 1 has dinitrogen tetroxide. And notice that that is one of the things in our overall reaction. But the problem is, in reaction 1, it's a reactant, and we need it to become a product. So what are we going to do to reaction 1? We're going to flip it. So I'm going to rewrite it and write 2NO2 is going to give us N2O4. And because I flipped that, I'm going to flip the sign of the enthalpy, and I'm going to make it a negative. All right, and what I like to do is when I get something in the right place with the correct coefficients, I like to circle it, so I know that that one's fixed. All right, let's look at the second reaction. What does it have in common? It has the nitrogen monoxide, and it has the oxygen, and they're on the correct side. And they actually also have the correct coefficients. So I'm just going to leave them alone. 2NO plus oxygen is going to give you 2NO2. And because I left it alone, I'm just going to leave the enthalpy as negative 112. And my nitrogen monoxide is correct in the correct side and has the correct coefficient. My oxygen is on the correct side, has the correct coefficient. And let's look at what's going to happen with the things that are left over. We have 2 nitrogen dioxides as a reactant in the first step, and we have 2 nitrogen dioxides as products, and so therefore they cancel out. And we end up with an overall reaction of 2NO plus oxygen gives us N2O4. And so all we're going to do is add up the enthalpy here. And so we're just going to add them together. And so we end up with negative 57.9 plus negative 112, which gives us negative 169.9. And the units, kilojoules per mole. And so we just add the enthalpies together, and that gives us the enthalpy of the overall reaction. So let's look at a practice problem. Our overall reaction is 2 carbons plus hydrogen making C2H2. And we're given the following stepwise reactions. And we're going to try to flip and multiply to get them to add up. In this case, we end up with 3 reactions that we're going to have to deal with. So let's start flipping and multiplying. So looking at the first reaction, well, what do we have in the first reaction? We have the C2H2, but it is a reactant, and we're going to need it to be a product. So the first reaction, we're going to have to deal with flipping. All right. Second reaction, we've got the carbon as a reactant, and that's what's in common with the overall reaction. So it's in the right place, but the problem is the coefficient is wrong. So we're going to have to do some multiplying for that one. And the last one, we have hydrogen as a reactant. It's on the correct side. It has the correct coefficient. So for that reaction, we're not going to have to do anything. So let's write it out and work it out. If it's a multiple choice, you don't have to write it all out, but to get some practice, you might want to start by writing it all out. So first reaction, we're going to flip. And so when I flip it, I get 2 carbon dioxides plus water. And watch your states, because the states will matter, especially when you're talking about water. gives you C2H2 plus 5/2 oxygen. And so since I flipped that reaction, I'm going to flip the sign of the enthalpy. And this is in the correct spot, and it has the correct coefficient. For the second one, I had to multiply it to get the correct coefficient for the carbon. So I'm going to say 2 carbons plus 2 oxygens give me 2 carbon dioxides. And I'm just going to take that enthalpy, negative 393.5, and for that one I'm just going to multiply it by 2 because that's what I did. And I'm going to circle my carbon because it's in the right spot and has the correct coefficient. For the last reaction, didn't have to do anything, just hydrogen plus 1/2 oxygen gives you water that is a liquid, which is important here, and it's negative 285.8. And my hydrogen is what I wanted it to be. Now let's check everything else and make sure it all cancels out. So when we look at, we have 2 carbon dioxides in the first reaction, and the second reaction we produce 2 carbon dioxides, so they cancel out. We have 1 water in the first reaction and 1 water in the last reaction, so they cancel out. And what about my oxygens? In the second reaction, I have 2 oxygens. In the third, I have 1/2, and that's 2.5 oxygens. And in the first, I produced 2.5 oxygens. So my oxygens cancel out. And now all I have to do is add up my enthalpies and get my overall enthalpy, and I find out that my overall enthalpy is positive 226 kilojoules per mole. So we did a couple of things here. In the first reaction we flipped, and when we flipped we had to change the sign. In the second reaction we had to adjust the coefficients, and when we adjusted the coefficients we just multiplied the enthalpy by that adjustment. We doubled the coefficients, we doubled the enthalpy. The last reaction we didn't have to do anything, it was all good. And so once I get everything lined up and everything adds up to the overall reaction, just add up your enthalpies and you'll get your overall enthalpy of the reaction. Now, some of you might have gone, well, why were there fractions in those overall in those step reactions? Because when we were in, introduction to chemistry, we were taught we can't have fractions; we had to have whole numbers. Well, that's because some of those reactions were written as formation reactions, and a formation reaction is a reaction that forms 1 mole of a compound from its elements in their standard states. And that's what that little, it looks like a degree symbol is for. It's not a degree symbol, it's called a knot. And you see it right here in our enthalpy symbols. That indicates we are at standard conditions. So the pressure is 1 atm, the temperature is 298 Kelvin or 25 degrees Celsius. So like water or carbon, you have to know what state they are in at standard conditions. Carbon would be a solid, hydrogen would be a gas at 25 degrees Celsius, 1 atm. So enthalpies of formations can be used to calculate the enthalpy of a reaction also. One thing to note, by definition, the enthalpy of formation of the most stable form of an element is 0. So sometimes you go and you look up enthalpies for elements and then you realize, oh, it's not there, it's 0 because, well, it's an element in standard state. So let's look at a formation reaction. The example of a formation reaction is the formation of ethanol. We have the formation of ethanol here. And we can see that the formation reaction shows forming 1 mole of a compound, ethanol, from its elements. So what elements did we include? We included carbon, hydrogen, and oxygen, because those are the three things that you will find in ethanol. And then we balance the coefficients to equal 1 mole of ethanol. So we have 1 mole of carbon, 2 moles of hydrogen, and 1/2 mole of oxygen, and that's going to give us our methanol. So let's write the formation reaction for water. So what are we forming? We are forming water. And we're making sure that we balance this for 1 mole of liquid water. And what's water made from? What elements does it come from? It comes from diatomic hydrogen and diatomic oxygen. At room temperature, hydrogen is a gas, oxygen is a gas, and now we need to do some balancing. We need 1 hydrogen, and we're going to need 1/2 oxygen to balance out the oxygens. So why do we need to know about formation reactions? If we know the enthalpy of a formation reaction, we can actually use that enthalpy to calculate the enthalpy of an overall reaction. We can use formation reactions with Hess's law to determine the enthalpy by flipping and multiplying the stepwise reactions if we use the formation reactions. Or if we know the enthalpies, we can just use this equation that we have here. This equation is found on your equation sheet, and the equation is the enthalpy of the reaction is equal to the sum of the enthalpy of the products. That's what this Greek letter sigma stands for. The sum of the enthalpies of formation of the products minus the sum of the enthalpies of the formation of the reactants. This equation right here is definitely on the AP equation sheet. But one thing you can remember that it goes in alphabetical order. It's products minus reactants, which we've already seen before. So we're going to add together the enthalpy of the products, and we're going to add together the enthalpy of the reactants, and then when we subtract the two, that will give us the enthalpy of the overall reaction. So let's look at a couple of examples, and we can look at how we can calculate the enthalpy of a reaction just knowing the enthalpy of formations. Know that the enthalpy of formations will be given to you in the form of a data table, or if you're using a textbook, you can just look them up in the back of the textbook. Know that they're temperature specific, and so we have that little naught symbol up there, which means these are measured at 298 Kelvin or 25 degrees Celsius. And also know that they are state specific. So when you're looking up water, make sure you're looking up the water in the correct state. So like in this one, we are dealing with water that is a liquid. So we need to make sure that we use the enthalpy of water as a liquid. So in this reaction, we're taking methane, we're reacting it with 5 moles of oxygen, and we're going to get 3 moles of carbon dioxide and 4 moles of water. So given that, we are going to use those stoichiometric coefficients and the enthalpy of each of these things, and we're going to be able to calculate the enthalpy of this overall reaction. So first, let's look at the equation. So the enthalpy of the reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of the formation of the reactants. So here we see in the first part, I just wrote out what we are going to be calculating. So our products are carbon dioxide and water. And so we're going to look up the enthalpy of formation of carbon dioxide, multiply it by 3. Why 3? Because that is the stoichiometric coefficient. Look up the enthalpy of formation for the water. Make sure we're using the liquid water. And we're going to multiply it by 4 because, again, it's the stoichiometric coefficient in the equation. Subtract. Make sure that you're subtracting. That's really, really important. 1 times the enthalpy of formation of the methane plus 5 times the enthalpy of formation of the oxygen. Now, once I have that set up, I can just substitute in the values. So I either look at the table or go back to the back of my textbook, and I find the enthalpy of formation for carbon dioxide is negative 393.5. And the enthalpy of formation of liquid water is negative 285.8. Substitute that. The enthalpy of formation of the methane is negative 103. And then if you do happen to go look it up, you'll find the enthalpy of formation of the oxygen is 0. Well, why is that? Well, that's because it's an element in its standard state. And we said the enthalpy of formation of the elements in their standard states are 0. So you don't necessarily have to write this out, but it's good to make sure that you're keeping track of it. So now that I have the values plugged in, I can just type all of that into my calculator. Make sure that you are following orders of operation. So add up your products, add up your reactants, and then make sure that you subtract them. Because if you forget to subtract them, then your signs are going to be wrong. And you end up with negative 2,219.85. And that should make sense because look at this reaction. Well, what are we doing? We're burning propane. And because we're burning propane, it's a combustion reaction, it should be exothermic. And that's what we found. We got a negative number. So let's do some practice. We're going to practice with a couple of reactions and see if we can do the calculations. You're going to have to look up some of these numbers and make sure that you can calculate the numbers. Get the numbers from either looking up in your textbook or if it's a actual problem, they'll be given to you. So first, let's calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide and water. We're going to do that one. So what's the first thing we need to do? Got to write the balanced equation. So what's the balanced equation? We're taking benzene, C6H6, and it's a combustion, which means we've got to react it with oxygen. And they're telling us what we're forming. We're forming carbon dioxide, and we're forming liquid water. Pay attention, that's important. All right, we need to do some balancing. They're telling us they want us to calculate it for 1 mole, so we're going to make that 1. And as a result, this ends up being a 6. And the water ends up being a 3. And therefore, to balance out the oxygen, we're going to have 15 halves oxygen to make those balance. Now we're just going to plug that stuff into the enthalpy calculation. So the enthalpy of the reaction is equal to, let's start with the products, 6 times the enthalpy of carbon dioxide plus 3 times the enthalpy of formation of the water. Now we'll deal with the reactants. Minus 1 times the enthalpy of formation of the benzene plus 15 halves the enthalpy of formation of the oxygen. Then we just go look up the numbers and substitute in the numbers. So I go look up the carbon dioxide, and I find carbon dioxide is negative 393.5. And the water is negative 285.8. And the benzene is positive, don't lose your signs, 49.2. And the oxygen element is 0. Now we just calculate that out and type all that into our calculator, and we get an enthalpy of a reaction is equal to negative 3267.6 kilojoules. Does our sign make sense? Yes, because again, this is a combustion and it is exothermic.